So my name is on this talk, but I'm working with just a bunch of other people on this Integrated Ocean Observing System project, which has a much larger scale. I'm going to be showing you one aspect of it. So all these folks here, Felipe Fernandez in particular in Brazil is helping work on this particular ocean model assessment project. Now this figure actually I used last year at SciPy, and I was talking about access to ocean model information. This is a picture of tidal currents in the black arrows flowing out of Boston Harbor. So this is the ebb tide flowing out of Boston Harbor. The colors here are the water depth. So this is a nice snapshot. It's actually a forecast model that's running all the time as part of this, funded by this Integrated Ocean Observing System. So you might wonder, well, how good are models like this? How well is it doing compared to actual data? So that's what I'm going to be talking about today. Basically build an infrastructure that we're developing that makes it really easy for people to compare models. And that's really important because it's a huge problem. Depending, your idea of a skill assessment for a particular model depends on the particular problem that you're trying to solve in the particular region that you need it solved. So we need lots of people doing this kind of work. Okay, so we might be interested in how well these models are doing at simulating particular events, like how well were they doing on the waves and the water levels during Hurricane Sandy, dramatic picture from New Jersey, or for the Deepwater Horizon spill. Here's a satellite image showing the complexity of how the spill evolved over several days and weeks. How well were the surface currents doing in terms of moving this around? How do these ocean models work? How well are they doing, and which ones are doing better when? So, just a word about the Integrated Ocean Observing System. If you haven't heard about this, it's a pretty cool thing. There's 17 different agencies, federal agencies, 11 different regional associations around the U.S. And the idea is that in any one of these regions, there's local issues that are important, but more importantly, perhaps, well, no, not more importantly, but there's a lot of different folks making measurements in the ocean and a lot of different people running models. So academics, state and local governments, as well as feds. And how would you put all that information together to solve some issues that are important to people in these different regions? So they've got a big challenge, the Integrated Ocean Observing System, in terms of how to bring all this information together. So they spend a fair amount on data management and building infrastructure. So this is what they do. Their core principles are to use open standards and practices, of course. The Open Geospatial Consortium, which I guess about 5 of you guys know about from Richard's question. ISO, I think you all know about that. And we also use standards, community standards that have been developed by Unidata. Those are the NetCDF guys. So we use a bit of their infrastructure as well. And basically, if you want to participate in IOOS, you're a data provider, you've got observations or models, you need to use web services. That's the way this distributed system is designed. And the data objects that we're trying to share through these services can be a little tricky. This is a curvilinear. This is a model showing a vertical mesh. So each one of these grid points, the model is computing things like temperature and salinity, and this is going up and down. And then you can tell by the spacing of these arrows that the grid is not uniform in the horizontal. So it's kind of a tricky but well-defined data blob. If you wanted to extract something like water level or temperature from one of these models, and you wanted to get the latitude, longitude, depth, and time out, you need a data model that supports that. And we also have these triangular mesh models. So in these models, you need to know things like how are the nodes of these triangles connected, and do you have the data at the center or the edges of these nodes? So we've got some tricky data types, but not totally unmanageable. And then we've got actual observations. We've got buoys out in the ocean measuring time series and measuring profiles that also vary in time. We've got ships running around making measurements and ocean gliders going around. So we have trajectories, things like that. But still, it's a manageable, sort of countable number of different data types: structured grid, unstructured grid, trajectory, time series. And those are things, by the way, that it's not just limited to ocean data, right? So if you have time series, profiles, grids of information, all the same stuff could work for you. It's not limited to just the ocean. In fact, we're ripping off most of the stuff from the Met and climate community. So you mentioned the climate conventions, CF conventions, climate and forecast conventions were mentioned before. These conventions provide a way for you to specify the metadata, attributes in your file that allow you to represent these different types of data like structured grid or unstructured grid or trajectories in a common way. So you put, if you want to put the files on disk, you could write a NetCDF file and put attributes into those NetCDF files that would fully describe those in a common way so that clients can work with them without knowing which particular model produced this data. Okay, so this is used by a bunch of different organizations. And so for IOOS, these are the recommended web service encodings. For in situ data, we use the OGC sensor observation service, which probably a lot of you haven't heard about. But I'll talk about it just in a second. But it delivers XML or CSV as output. And then for gridded data, this OPENDAP with climate forecast conventions. And this is like accessing NetCDF files over the internet. Essentially, you can extract just the data you need out of them and the attributes as well. So it delivers a binary payload. And the images, I'm not going to really talk about today. So OGC sensor observation service, actually Richard mentioned this briefly, you get capabilities, you can then describe, this is common to all OGC services, then you can describe the sensor, so you can actually find out information about that particular sensor, it'll tell you about the sensor, and then you can grab data from that sensor through a GetObservation request. And this is what one of these things looks like, long URL, but you say something like, okay, here's the endpoint, get observation, what do you want? You want water surface height above reference datum. This is the particular station, the response format, text CSV, the event time, range here, and the vertical datum here, we're specifying in an EPSG format, which is actually the NAVD88 vertical datum, and then we want data type, preliminary 6 minute. This is all stuff that you learn from the get capabilities when you say, when you get capabilities, and so you can find out what all these things are that you can then query for. So this is what this is what the providers can do. So there's a bunch of people collecting information. They might have models. They might have observed data. They can throw them in NetCDF files on their file system. They can install this thing called the THREDDS data server from Unidata, which is actually is a Java application. But if they put this on there, it can point at all these files and convert them into a common data model. If they're not already in CF convention, you can add this little layer of XML here, converts it into a common data model, grid, UGrid, time series, and then depending on these, so it's like, this is like a common outlet that you're plugging things into then, right? So you've got a common data model in software, and then you can connect these services like OPENDAP-CF, and here's the sensor observation service if you have, sensor data. And down here, we have an ISO metadata service that actually takes the metadata information from those different data sets and delivers it as ISO metadata. The ISO metadata then can be ingested into these catalog harvesting systems. There's a bunch of these that all perform pretty much the same job. You may have heard of these, like GeoPortal servers, GeoNetwork, GICAT, CCAN with PyCSW. All of these things harvest data from servers that are all over the place, put the metadata in a database, and it looks something like this. So this is so now we have a common data model for metadata, ISO metadata in a database that's being harvested from all these different sources on the web, different kind of web services, THREDDS, OPENDAP here, NetCDF down here, web services, different kinds of web services here, and then you can query these things using either OpenSearch, which is a sort of simplified query tool, or a more complex CSW, this OGC CSW service. So we've got a way to search a catalog. Now, how do we actually get the data? The British Met Office has built this wonderful IRIS package that actually, so they've got CartoPy and they've got IRIS. If you actually install IRIS, you get CartoPy for free. That's actually, so it integrates nicely with that. But for us, what it does is it understands all this CF convention stuff. So you can go to one of those OPENDAP URLs with CF conventions, put it in here, say IRIS load, and you get back a list of all the different variables in the file, just kind of looking like NetCDF, maybe an NC dump or something, except now you can take any of these variables, and because it understands the CF conventions, you can just say, hey, give me a slice at a particular time step, and in this latitude and longitude range, and then just plot it up using CartoPy. And so there's nothing model specific here, notice. This is just that you've standardized this web service, and now you can access it, and it understands what the time is and the latitude and longitude without you having to point at different variables and muck around. So it's really nice. So for the SOS and CSW services, we use this really cool package, OWSLib. This is led by Tom Krilitis. There's something like 20 developers on this. Actually, I happened to snap this screen grab when it was up with a $1.62 million in development so far, I guess. And it supports a bunch of OGC services. This is just like the top 7, and there's a longer list. But it supports SOS and CSW. So we're using it for those 2 things. So, and then the last thing we're using is a sort of a convenience sort of toolkit called IOOS, which is pretty, okay, so this is the one you might not use. This is the one that's pretty specific to metocean stuff, and it basically does things like, okay, so you could use OWSLib to get data from a sensor observation service, but maybe that sensor observation service only gives you like 4 days of data at a time, and you want users to be able to ask for 3 weeks. And so this will go, make those OWSLib requests behind the scenes to pull that stuff back. So it goes after data providers that are well known and well used, I guess, in the community, you might say. So, so then putting this all together then, in this system test, we're building IPython notebooks that demonstrate how all this stuff works. So that, I mean, they're web services, so people could do this in any language, right? In MATLAB or ArcGIS or whatever. But we want to demonstrate in Python how this all works. So we have these IPython notebooks, and this is one on inundation. This is actually looking at water levels. So the idea here is the user comes in and specifies some date range here, and they specify a bounding box of interest. That's the only input to this little notebook. So you specify some bounding box time region, say in this case, maybe from the last 3 days to the next 3 days in New England. You say go, and it goes off, and then the first thing it does is it does a CSW request to the catalog and finds all the data sets that have water levels in them in that geospatial range and in that temporal range. Brings back all the metadata objects, okay, and then you can go through those metadata objects and pull out those data endpoints, either SOS endpoints or OpenDAP endpoints, and then just start working through because you know how to read those. So there's no like, you go to data.gov and you do some search and you get landed on some web page and there's a README and so we're trying to get away from that to really go to automated, basically, systems. So you specify that, and it finds all these, and I've specified this region here, and we're using a CartoPy plot here just to plot out the stations that it found. Okay, it found all these from doing a catalog search, and then we actually go into we pull the data from each of these using SOS, and we have time series, which we put into pandas, and we interpolate to a common time base, 6-minute interval, and then we dip into all the model output we found, and we use IRIS to load the model output, find the closest point to these station observations, pull a time series from all the models, put it on the same time base as the observations, and I'm not showing you the whole notebook, but it's all in a single notebook. And finally, at cell 45, you get a big list of plots from all these different stations. And so this gray line is the observations. I did this on July 3rd, this particular one. And these are all the different models that it picked up. So it picked up 4 different models. Actually, this is a particular location. This was Hurricane Arthur, which was predicted actually to set the water level down at Montauk. I have to go back and look at how well the models, the observations, how well that agreed with observations. But anyway, so this is just a line plot. You might go, Jesus, that's a lot of work for just a few lines on a plot. But what's going on behind this is pretty remarkable, I think. And so if somebody puts a new model online, those services get harvested, and a new plot will just appear on this the next time I run it, because it'll just pull that. So it's all dynamic. There's no URLs that are being, that I'm going to have to go change if one of them goes down or something. It's all hit from a catalog search. So we've got the notebook. That's awesome. People can use that, but we've got some kind of unusual packages or some hard to build packages. Like Iris is not particularly easy to build, and we've got these other things. So. We've been building Conda packages and uploading them to Binstar. So this really should be the IOOS group, but this should be the IOOS organization here. But right now they're on mine. But there's a whole bunch of stuff here that we've used, and some of these are packages that are around elsewhere. But we wanted the most recent version, and we wanted to make it easy for people who are using Conda to just say Conda install this thing. Okay, so we've done that, and of course all the recipes are on GitHub under the IOOS under the IOOS organization. And then finally, we've been using Wakari to basically make it super easy for people to get and run these workflows. So this is an example of using, I don't know if you've not heard any Wakari talks yet, but if you have, in Wakari, you're running a notebook on the cloud, you log into your environment here, your username is up here, and you can select a particular environment, different Python environment. You can create your own custom Python environment. So here we've installed the PyOOS package and created a PyOOS environment. It's just a few packages in PyOOS. And so we wanted to create a notebook that uses PyOOS, makes a plot, grabs some data, makes a plot. Then we can share this. All we have to do is go over here and click share. When we click share, we get a URL. We actually get an opportunity to share our environment, so we can share that PyOOS environment, and that gets bundled up. URL, somebody, you pass this to somebody an email, they can see what you've done, but they can click this green button, run edit this notebook. They get prompted to log into Wakari. If they don't have an account, they can just register for free, no credit card required. And then it says fetch a bundle, fetch this bundle, and then environment. Do you want to install this environment? If you say yes, it'll install your environment. Okay? So, and then they're running your notebook without installing anything on their computer, just using their web browser. And that's about as reproducible as you can get. So that's been huge for us, actually, in getting people to actually try this stuff and use it, the combination of Binstar and Wakari. And so I just wanted to point out where we're headed. We've got, this is one little test case here, but we've got a bunch of other things that we're developing in notebooks. These are all in notebooks. They're all on GitHub. You can take a look at them right now and see where they are. Some of them are just actually in the dream stage, I think. And so also where we're going, though, in this model data comparison is we're going to track this paper that was put out last year about skill assessment of models in the Mid-Atlantic Bight by John Wilkin and Eli Hunter. And they did vertical sections through these different models using MATLAB, observations on the top, and then these sections through these different models, and did quantitative statistics based on that. So these could be MET models, hydro models, whatever. But anyway, we want to reproduce this kind of thing in Python notebooks, and then basically set the notebooks or the Python code behind the notebooks up to deliver these products into sort of a dashboard on a web page. So, and then we also want to compare surface currents. We've got HF radar measurements in a large part of the coastal ocean to measure the surface currents so we can compare to model output. They did this in their paper. We want to do the same thing in Python. And to do that, we're probably going to be using some of these different display capabilities like this is MPL leaflet. We've been playing with this a little bit. So instead of CartoPy here, we're making a plot using MPL leaflet. And then, of course, you can zoom in on this plot interactively in the notebook and see the model output compared to the data. And finally, we've been also playing around with Folium and Vincent so that instead of that plot in CartoPy with just the stations, these are now, if you click one of these, you can zoom in on these stations for one thing and see, oh, yes, this is actually on the end of some pier, because the map will zoom, zoom, zoom. And then when you click on the station location, up will pop a little plot. Need a little work down here on the labeling. But this little plot pops up from Vincent, which was just dumped out of a data frame here really easily. So these two packages, Folium and Vincent, work really nicely with Matplotlib and with Pandas. So finally, UGrid, unstructured grid data. It worked. Actually, you can load unstructured grid data into Iris. That's what we did for that example. But it doesn't know about how those triangles are connected. We just went for nearest node, and that's why that worked. So last year at SciPy, we had a little code sprint and developed this little PyUGrid package. It's sort of very young. And we're hoping to make some more progress on that. But I would love to see this integrated into Iris itself. So, in summary, we do have a framework that really allows assessment for anyone. Python gave us the capability for analysis and visualization. The notebook gives us a way to document the whole thing. And Wakari gives us and tools like it give us the ability to reproduce the workflows. And and it really is, I think anyone who has a web browser right now can go do this. They can run that notebook that I showed. They can change the location to the West Coast and some other time period and be looking at how well the models are doing there. So I'm very excited about this, and I think it's going to result in the better use of models in general. People are going to understand how they work. We get back to the modelers and say, hey, you have a vertical datum problem, and they make a better model, and the result is a better world. Thank you very much.